Hello, in this video we're going to talk about continuous functions. First we start with the definition of a continuous function, what it means for a function to be continuous at a point. Then we'll discuss some examples of functions that are continuous and are not continuous. Then we'll talk about some of the main properties of continuous functions. So throughout this chapter, the domain of each function is a subset of real numbers, and I usually use the domain with a capital letter D or D1 or D2. First, what is a continuous function? So the way you have learned about continuous functions is that if you are trying to draw the graph of this function, you have to be able to draw it without lifting your pen from the paper. However, that's not a very accurate way of describing what a continuous function is. What it means for a function to be continuous, and I will talk about why that is not very accurate. What it means for a function to be continuous is that if you have a point, whenever you get close to this point, your functional value gets close to the functional value of f of x naught. What does that mean? It means if I have a sequence xn approaching x naught, then f of that sequence xn approaches f of x naught. So here is the definition. Let x naught be a point in D. A function f from D to R is said to be continuous at x naught, provided whenever xn is a sequence in D that approaches x naught, the sequence f of xn approaches f of x naught. Otherwise, we say f has a discontinuity at x naught, or f is discontinuous at x naught. We say f is continuous over D if it is continuous at every point in D. Okay, so now we will look at some examples. The first example is an example of a continuous function. Every polynomial is continuous over the entire real numbers. Let's go over the proof of this one. So in order to show that every polynomial is continuous over the entire real numbers, by definition we will have to show it is continuous at every real number. So let's start with some real number r. Now in order to show f or the polynomial is continuous at r, we will have to show if xn is a sequence that approaches x naught, then f of xn also approaches f of x naught. So suppose p is a polynomial, and an is a sequence in R with an approaching R. We will have to show p of an approaches p of R, but this is something we have actually done before by properties of limit. So by properties of limit of p of an is equal to p of r as n approaches infinity. Thus p is continuous at r. So we showed that p is continuous at every real number. Therefore p is continuous over the entire set of real numbers. Bottom line is this statement that p of an approaches p of r, and that's something we have discussed before. Okay, so that's an example of a continuous function. Next, we're going to talk about an example of a function that is not continuous or discontinuous. This one is called the Dirichlet function. So first, what is the Dirichlet function? And next, how do we prove that it is discontinuous everywhere? The Dirichlet function is a function that gives you 1 at rational points. So at 0, at 1/10, at any of the rational numbers, we'll get a point up here. Of course, there's like infinitely many points, a dense set that is up there. And at every irrational, for example, root 2, pi, all of these numbers that are irrational, you would get a point at the bottom. So if you take any point, if you take a point, let's say x, you can approach x along irrationals because of the fact that it's dense. The set of irrationals is dense. And you can also approach x from the set of rationals, which is why it cannot be continuous, because on top you would get 1, at the bottom you would get 0. So f of x must be both 1 and f of 0, and 0, which is not possible. Okay, so in order to show it is discontinuous, we are proving negatives. We are trying to prove it is not continuous. So proving negatives, it makes sense to use proof by contradiction. So on the contrary, assume f is continuous at some real number. Perhaps I will call that x naught. Now, since q is rational, since q is dense and q complement are dense, are both in fact sequentially dense. At this point we know dense and sequentially dense are the same. Every set that is dense is also sequentially dense, and vice versa. Since q and q complement are both sequentially dense, there are sequences an in q and bn in q complement such that an approaches x naught and bn approaches x naught as well. Now we know that an and bn, we know that f is continuous at x naught. Since f is continuous at x naught, we must have limit of f of an equals f of x naught as n approaches infinity, and also limit of f of bn is f of x naught as n approaches infinity. Now we know f of an is 1, so this is because an is rational, and f of bn is 0 because bn is irrational. We obtain that f of x naught is 1, so this is 1, so f of x naught must be 1. This is 0. If you go back, the definition was for every rational you get 1, for every irrational you get 0. So at the same time f of x naught must be 0 and 1, which is a contradiction. So what we did was we assumed f is continuous at a point and we got a contradiction. Therefore f is continuous over the entire real line. Okay, so we looked at an example of a function that was continuous, polynomials. In fact, a set of functions that are all continuous. And we looked at a function that was in fact not continuous anywhere. Let's look at a third example. This is a very interesting example. This brings me to the fact that I said at the beginning, which is saying that a continuous function is a function that whenever you want to draw the diagram, you shouldn't be lifting your finger, lifting the pen. That is not completely accurate. So let me tell you why that is the case. If you look at this function from 0 to 1, it gives you 1, it gives you, x So this is the function, and from 1 to 2, that's not in the domain, and from 2 to 3 we get a different function. We get x plus 1. So at 2 we get 3, and it's a slope 1 line, so it would be something like that. So this is our function. This is the graph. Now we want to see at what points it is continuous. So here we know that it would be continuous. If you have something here, when you're approaching to this point, it would be continuous. And also here the same way. You might be thinking that there's a point of discontinuity at point 1, because when you're trying to draw the diagram at 1, you have to lift your pen and then continue. You have to lift your pen and continue on the other side. However, this is in fact continuous at 1 as well. And the reason is, if you think about how you would check if something is continuous. The way you check if something is continuous or not, you show that if a sequence approaches x0, then f of that sequence approaches f of x0. If you have a sequence approaching 1, the sequence cannot be here. It would have to be between 0 and 1. After a point, it would have to be between 0 and 1 because of the gap that we have between 1 and 2. Therefore, the sequence is going to be, f of that sequence would approach f of 1. Okay, so you kind of see that what I'm getting to. What I'm getting to is that f is continuous on its domain. So it's continuous everywhere on its domain. So we will have to do it in two different cases. First, something inside the interval 0 to 1, and then something inside the interval from 2 to 3. So assume x0 is in the interval from 0 to 1. We will prove that f is continuous at x0. Let an inside the union of these two intervals be a sequence that converges to x0. Now, since x0 is between 0 and 1, the sequence must be inside 0, 1 at some point. How do we articulate that? What we're going to have to do is to take some epsilon, and we have to take epsilon to be less than or equal to 1. So let epsilon be 1 in the definition of limit. So there is some natural number n such that for every natural number greater than or equal to n, the distance between an and x0 is less than 1. So this means an is less than, and I don't really care about the other side, an is less than x0 plus 1. But an is at most 1, so this would be less than or equal to 2. So this means an is less than 2, and we also know, so since an is either in this interval or in the interval from 2 to 3, we have that. So it's either from 0 to 1 or from 2 to 3. It is not in the interval from 2 to 3 because it's less than 2, so it's not here. Therefore, an must be between 0 and 1. And that means f of an is just, if you look at the definition of f between 0 and 1, f of x when x is between 0 and 1 is x itself. So that is equal to an itself for all n greater than or equal to n. And this means when you take the limit of f of an, that's the same as, since as we have discussed, when you're dealing with a sequence, you can ignore the first terms, the first few terms, finitely many terms. This is exactly the same as the limit of an. And limit of an, as we discussed, is x naught. So that tells us, and of course, f of x naught is x naught, since x naught is between 0 and 1. So therefore, f is continuous at x naught. The other interval from 2 to 3 is very similar. So similarly, f is continuous at x naught when x naught is in the interval from 2 to 3. So this completes the proof. So what we did was we showed that f is continuous on its domain. We showed it is continuous from 0 to 1, and from 2 to 3 is a very similar process. Okay, so next we're going to talk about some properties of continuous functions. So as I said, we started with the definition of continuous functions. Then we did 3 examples. Now we're going to talk about some properties of continuous functions. Okay, so first the definition of sum and product of 2 functions. If you take 2 functions f and g with the same domain, their sum is what you expect it to be. F plus g of x is f of x plus g of x, and their product is again what you expect it to be. F times g of x is f of x plus a times g of x. If g of x is non-zero, then you can also talk about their quotient. Their quotient is again what you expect it to be. It's f of x divided by g of x. Now, if f and g are continuous at a point, then their sum and their product is also are also continuous. So suppose x naught is a point in D. F and g from D to R are continuous at x naught. Then so are f plus g and f times g. So if you have 2 functions continuous at a point, then their sum and their product is also continuous at the same point. Furthermore, if the denominator is non-zero, if g of x is non-zero for all x in D, then f over g is continuous at x naught. Okay, so we will go ahead and prove this one. In order to show f plus g is continuous, we will have to take a sequence that approaches x naught and then show that f plus g of that sequence approaches f plus g of x naught. So let an in D be a sequence with an converging to x naught. Since f and g are continuous at x naught, limit of f of an is f of x naught as n approaches infinity, and limit of g of an is also g of x naught as n approaches infinity. If you look at the limit of f plus g of an as n approaches infinity, this is the limit of, by definition, this is just f of an plus g of an as n approaches infinity. Now, we know limit of f of an is f of x naught, and we know limit of g of an is g of x naught. So here I'm using properties of limits. Because I know limit of sum is sum of limits, assuming that those two limits exist. And of course this is just f plus g of x naught. And that implies f is continuous at x naught. F plus g is continuous at x naught. So there is really nothing new here. The only thing is new here is the definition of continuity. So what is new here is the definition of continuity. Because the main thing is properties of limits that I'm using here. And then it's the exact same process for product and sum. So similar proof, a similar proof works for fg and f over g. And the reason is limit of product is product of limits, and limit of ratio is ratio of limits. So it's basically the same process. Okay, now suppose p and q are continuous, are polynomials. Let d be all of the real numbers that the denominator q of x isn't 0. Then p over q is continuous over d. And this follows from the previous theorem, because if you look at p, p is continuous. If you look at q, q is also continuous, because we know polynomials are continuous. And then we apply the polynomial continuous over continuous is continuous. So that just follows from the previous theorem and the fact that polynomials are continuous. Okay. These functions of the form polynomial over polynomial, these are called rational functions. The same way that if you start from integers and then divide integers, you call them rational numbers. Here, with the similar for the similar reason, we call these rational functions. Polynomials are obtained by only addition and multiplication. If you also get the division involved, you get rational functions. So a function of the form p of x over q of x, where p and q are polynomials, is called a rational function. The domain of such a function is the set given below. It is the set of all real numbers that the denominator isn't 0. We talked about how rational functions are continuous. So we have now created some functions that are continuous, polynomials, and then the next step was rational functions. And of course, polynomials themselves are rational functions with the denominator of 1. Okay, let's look at the last theorem for today. If you take two functions, f from d1 to r, so we have a function, the domain is d1 and the range is r, the codomain is r. And I have a function from d2 to r. So this one is f and this one is g. I would like to compose these. In other words, I want to put g after f. In order to be able to put g after f, we need their range, because what I want is I want to be able to talk about g of f of x. So what I need is I need x to be in the domain of f, and then I need f of x to be in the domain of g. Domain of g is d2. So what I need is the range of f to be inside the domain of g. So let's look at this theorem. Let f from d1 to r and g from d to r be two functions for which f of d1 is inside d2. So f of d1 is inside d2. So it's a function from d1 to r, and then g is from d2 to r. F of d1 is inside d2. suppose x naught, so we have a point here, and that's called x naught, is in D1. And we know that f is continuous at x naught, and g is continuous at f of x naught. Then the composition GOF, this is the composition GOF, is continuous at x naught. Okay, so we're going to go ahead and prove this one. In order to prove GOF is continuous, think about what we need to do. So what we need to do is we're going to have to start from a sequence that converges to x naught and then show that the functional value of that sequence also converges to the functional value of x naught. So suppose an is in the domain of GOF, which is D1, is a sequence converging to x naught. So now what I need to do is I need to show that limit of GOF is equal to GOF, limit of GOF of an. So let me write it down. We need to show limit of GOF of an is GOF of x naught as n approaches infinity. If you look at the inside f of an, that approaches f of x naught. So since f is continuous at x naught, limit of f of an is equal to f of x naught as n approaches infinity. Now, since g is continuous at f of x naught, limit of g of f of an as n approaches infinity is g of f of x naught. And that's why GOF is continuous at x naught. So if you think about this, this one is GOF of an, and this side is GOF of x naught. What we showed is that GOF of an approaches GOF of x naught, which is why GOF is continuous at x naught. Okay, so this brings me to the end of this video. So next time we'll continue our discussion on single variable advanced calculus. And if you want to continue with these videos, feel free to subscribe. I will see you in the next video.